For this lesson, we're going to be taking a look at a very important principle from trigonometry and for periodic functions, and it's something called the unit circle. To start with, we're going to just refresh our memories on special triangles because the unit circle is quite often shown in terms of some quantities that should be very familiar from special triangles. So special triangles are typically the 45 degree, 45 degree, 90 triangle, which has sides 1, 1, root 2. That's the proportion of those sides. We have the 30, 60, 90 degree triangle, which has sides 1, 2, root 3. At least that's how they're typically represented. But the important part with these special triangles is the proportion or the ratio of the sides. The actual numbers that we put here don't actually matter as much as you might think. So I'm going to start off, we're talking about the unit circle. In math and in physics, quite often we try to, if we have the option, we try to choose values that make our work as simple as possible. We try to boil things down to their purest form. So one way, so remember when we've talked about the special triangles, when we talked about trigonometric ratios, we've talked about x, y, and r. And so we're going to come back to that idea. So when I'm talking about r, I'm talking about the r from the x, y, and r definition in trigonometric ratios. And the r in particular is referring to the hypotenuse. So when I say, what if we wanted to force r to be equal to 1? What we're saying is, let's force the hypotenuse to be equal to 1. And what would that look like? Well, so long as we maintain the ratio of the triangle sides to each other, that's fine. So take this root 2, which is the hypotenuse. How do we turn that into the number 1? We would divide by the square root of 2. But I can't do that just to that side because then the proportions would be messed up. What I need to do is I have to divide all sides by root 2. And this is no different, and this is just as valid. I could have done this. I could have said, I'm going to take all sides and I'm going to just multiply them all by 5. That would also result in a valid triangle because the ratios between the sides would still be preserved, so this would still be a 45, 45, 90 triangle. But instead, I wanted to get a hypotenuse of length 1, so now root 2 over root 2 is 1, and 1 over root 2, it's quite often represented this way. Or it could be rationalized and written as root 2 over 2. You'll see it both ways. And it helps if you just become comfortable enough that you see both of them and you recognize them as being equivalent. In order to change my second special triangle into having a hypotenuse of length 1, I have to divide everything by 2. And so the new triangle, it's still the 30, 60, 90 triangle. Now it's got a hypotenuse of 1. This side is root 3 over 2. It doesn't need to be rationalized. It doesn't have a radical in the denominator. And this side is 1/2. Now, why am I spending time on that? What's the value in that? Well, first of all, I just wanted you to understand about that idea of proportionality, that we can scale these triangles however we want. The angles will continue to be the same so long as we are consistent in the way that we scale things. Now let's relate this to the idea of a circle. So hopefully you can see it. I used a computer to create this diagram. And so the triangle that I have here is actually the 30, 60, 90 triangle. 30 degrees, 60 degrees, and 90 degrees. It's just kind of tilted over onto its side. So the 30-degree angle is actually in that corner. And because we're now talking about angles in standard position, so you can see that my initial arm is along the x-axis, and then I've got a terminal arm So this triangle is representing a rotation of 30 degrees. So we arranged it so that the hypotenuse of that special triangle is 1, and we ended up with the other two sides. Once we changed the proportions so the hypotenuse was 1, then the short side over here was 1/2, and the long side here was √3/2. So that means that the point itself, well, it's going to have an x-coordinate, that's the length of this side, which is √3/2, and it's going to have a y-coordinate, which is 1/2. We can repeat that for the other possible locations for special triangles. This is the 45-45-90 special triangle. We arranged it so it had a hypotenuse of 1. So hopefully you can see now, well, why did we focus on that idea of having the hypotenuse be 1, the r value being 1, because that r value, that hypotenuse, is always going to be tracing out a circle of radius 1. And that really simplifies things for us. So now with that circle of radius 1, this is going to be 1/√2, and this is going to be 1/√2. And so the x-coordinate, which is this distance, is 1/√2, and the y-coordinate is 1/√2. Now, I want to start tying in something else here, because when we originally started working with the special triangles, regardless of what the proportion was, let's go back to the original form, 1, 1, and √2. Well, the reason why we worked with these was so that when you had something like the cosine of 45 degrees, you would be able to do this without a calculator and with an exact value. The cosine of 45 degrees is 1/√2. And the sine of 45 degrees, in this case for this triangle, turns out to also be 1/√2. And if you take a look up here, well, these coordinates, these x and y coordinates of the point on this circle match up to that 1/√2. So we've changed the proportion of the triangle, but this still seems to work out. Now I've introduced this idea while they're both the same. So let's move on to the next one, and let's maybe distinguish between them even more. So once again, now I've got the 30-60. I'm not going to label the 30 in the small angle. This is a 60-degree angle. And so once again, the r value is 1. This is the short side is 1/2, and the long side is √3/2. In this case, the short side corresponds to the x-coordinate, and the long side corresponds to the y-coordinate. And once again, I'm going to refer back to our original 1, 2, √3 triangle. That's how we originally learned it. And we're referring to this angle 60 degrees. So in terms of that angle 60 degrees, the sine of 60 degrees is opposite over hypotenuse. That's √3/2. And the cosine of 60 degrees is adjacent over hypotenuse. That's 1/2. So now we can see that this point is actually can be expressed in terms of this angle. The coordinates of this point are actually the cosine of 60 degrees, that's the x-coordinate, and the y-coordinate is the sine of 60 degrees. Now there's another subtle piece here, which is one of the things we're working with the unit circle. One of the conveniences of the unit circle is that the radius is 1. So this is actually 1 times the cosine of 60 degrees, and this is actually 1 times the sine of 60 degrees. So you can see there, instead of it being some other r value, it being 1 working with the unit circle just simplifies that. So in general, on the unit circle, the x-coordinate can always be expressed as the cosine of whatever your principal angle is, and the y-coordinate of a point on the circle can be represented as the sine of your principal angle. So I've basically already developed this. So the coordinates of any point on a circle can be expressed as, so that was what I was working through there. It's not just the cosine of the principal angle theta or the sine of the principal angle theta. We also need to include the length of the hypotenuse, or the radius of the circle. So the x-coordinate is going to be r cos theta, and the y-coordinate is going to be r sine theta. And as I already pointed out there, for the unit circle, the radius is equal to 1, which means any point is simply 1 cos theta, and the y-coordinate would be 1 sine theta. And this can be applied. We only worked, those 3 examples I gave you so far were in quadrant 1. So you can see I've laid out those first 3 triangles I did were in quadrant 1. But those triangles can be placed in any way. So I've given an example. So this first triangle that we did, this one had an x-coordinate of √3/2 and a y-coordinate of 1/2. That means that this point is going to have those same magnitudes for the x and y coordinates, but this point has a negative x-coordinate and has a negative y-coordinate. So this is actually the point negative √3/2, negative 1/2. But the actual magnitude of the numbers is the same. In blue, this was our 45 degree, and so that would mean over here, that would actually make this 45 degrees. So what would the principal angle be? That would actually be 135 degrees. And this point is going to resemble this point. So this one, just to refresh our memories, this one is 1/√2, 1/√2. And over here on this side, the only difference is that the x-coordinate is negative, but the y-coordinate is still positive. And this also ties in the idea of the cast rule, the difference between the x-coordinates and the y-coordinates, sometimes being positive and sometimes being negative. And then finally, this third point, this one had an x-coordinate of 1/2, and it had a y-coordinate of √3/2. Down here, this point, it's going to be the same. It's still going to have an x-coordinate of 1/2, but the y-coordinate is going to be negative √3/2. Now, what is that actually telling you? I want to tie this back in to what we were saying before. Don't forget that this represents the cosine. The x-coordinate represents the cosine, and the y-coordinate represents the sine. So what this is telling you, the way you tie these things together, as I mentioned, this is the principal angle of 135 degrees. So with this information, I actually know that the cosine of 135 degrees is equal to negative 1/√2. And the sine of 135 degrees is equal to positive 1/√2. Now you could have done this same thing using the related acute angle and the cast rule. So you could also, if you want to remember it a different way, the cosine of 135 degrees has a related acute angle of 45 degrees. So the cos of 135 is the same as the cos of 45, except for the cast rule says that cosine is negative here, so it's negative cosine of 45 degrees, which of course is negative 1 over root 2. So these things all relate back to each other. I also want to take this opportunity to talk about some very special cases, which is what happens when your points are either on the positive or negative x-axis or the positive or negative y-axis. So they're still on the circle, but they're on the axes themselves. Now remember that the radius of this circle is still equal to 1. But if the radius is equal to 1 along that line, it's also equal to 1 along here, and that means that the coordinates of that point are 1, 0. Over here on this side, the coordinates would be negative 1, 0. At the top, the coordinates of that point, it's got an x-coordinate of 0. All of the r value, all the length of the r value is in the y-coordinate. That's 0, 1. And then down here we have 0, negative 1. To put that another way, what this one is saying is that, take a look, we've got the first number, the x-coordinate is cosine. The cosine of 0 degrees is equal to 1. That's also the cosine of 360 degrees, by the way, because that's going around a whole circle. The sine of 0 degrees is equal to 0. And of course, that's the same as the sine of 360 degrees. And I could do that for any one of these. If I want to know, for example, let's just pick one at random, what is the sine of 270 degrees? Well, 270 degrees is down here in the negative y-axis. The sine is the y-coordinate of that point on the unit circle, so the sine of 270 degrees is negative 1. And you can work this backwards. You could also say the sine of theta equals negative 1. Well, working backwards, sine theta, the y-coordinate is negative 1. That only occurs here. And so that means that theta must be equal to 270 degrees. So there are lots of things you can do with an understanding of the unit circle. The unit circle is a very tough tool to make use of, but an understanding of it is very important and useful. There are many copies out there of the unit circle. They are varying levels of cluttered because what they're trying to do is very efficiently provide all of the information. This unit circle is one of the better ones that I've found. The problem with this unit circle, it's got degrees along the inner circle, so 0 degrees to 90 all the way around. It has another unit of measure called a radian, which actually is more typically used in both math and physics. It's covered in the grade 12 course. And this particular version of the unit circle, your x-coordinate and y-coordinates, you can see that they have been rationalized. So rather than writing this as 1 over root 2, they're writing these as root 2 over 2. Now that we've done that, now that we've worked through that, we could use that unit circle. We could also use our calculator for this part, which is to start to get an idea of what the graphs of sine and cosine would look like. But rather than do that, now if you were doing this in class, I would probably have you I'd give you a template and you would do it that way. But I've actually got something that I've put together that I'd like to look at. It's using Geogebra. And so I'd like to take a look at this instead. Let me just get the right copy open here. And this is a little web tool that I've got posted on my Geogebra page. I'll provide a link to it. And so let's take this idea. And let's start by looking at cosine, which is actually a little bit more convenient. So we mentioned that the cosine is the x-coordinate of the point. So right now, for example, the x-coordinate of this point C is 1. the y-coordinate is 0. If I start to change the angle, you can see I introduced the angle there. The value of cosine is decreasing. It's not 1 anymore because it doesn't reach as far. Some of the value is in the y-coordinate now. And so as I do that, the x-coordinate is going to come down towards 0, and then the x-coordinate is going to become negative. And you can see my angle has passed into quadrant 2. It's now an obtuse angle. I have a negative value for cosine. That's consistent with the cast rule. All the way over here, let's say I take it out to 180 degrees, if I can make it stick there. Not so easy to do. Close enough. Okay. And then it continues around that circle. And we're following just the x-coordinate of that point the whole way. Now we can see what that looks like a little bit better if I turn on tracing. And I repeat the process. Now I'm going backwards. But you can see the curve is smooth the whole time. Those little pieces that are missing is just because of how I'm moving this. If I move it back and forth, I can fill in all the parts of that graph. It just means that I'm moving it too quickly and sometimes it's skipping over a point. And so that is the graph of cosine. That's what it looks like when you graph cosine with respect to changing the angle. I can do the same thing with the sine curve. Now, what is sine interested in? Sine is interested in the y-coordinate of this point. And so it starts, you can see it starts at 0, and then it moves into the positive. It peaks at 1 because we're dealing with a unit circle. But technically, notice how I haven't labeled this as a 1 or a -1. This peak is r, whatever r happens to be. It's just normally we do it as 1. And then sine starts to fall off, meaning the y-coordinate over here is getting smaller. And then it moves into the negatives, and then it's going to end at 0. And you can see those two curves follow the exact same shape. Where they start their shape is a little bit different. It's offset. But other than that offset, they are the same shape for sine and cosine. Sine and cosine just track the x and y, or I should say it this way, cosine and sine track the x and y coordinates around the circle, whether it's the unit circle or a circle of radius r. Okay, so I think that's enough for the video for now. So I'm not going to graph this by hand, and then I'm just going to finish up with your assigned work, which I believe is up to date as of, well, of course, the making of this video.